this video, we will learn finite difference method. We will learn about this difference method first, and later we will see how we can implement the finite difference method using Scilab. So this finite difference method is used to solve the second order differential equations of this type. So this is the general second order differential equation. So if we have to solve such kind of a differential equation with the boundary conditions given to us, say at x equal to a, the value of y is alpha, and at x equal to b, the value of y is given to us and it is beta. So with this boundary condition given to us, let us see how we can solve the second order differential equation using finite difference method. So in order to solve the differential equation using this finite difference method, we have to replace the second order and the first order derivative appearing in the equation with the finite difference approximations. So if we make use of the central difference approximation, then the second order derivative, that is y double prime x, is replaced by this approximation. And similarly, the first order derivative using the central difference approximation can be approximated by this difference. So if we make use of these approximations for the first order derivative and the second order derivative in the given differential equation, which we have to solve for the given boundary conditions, we can simplify the equations using the finite difference method. So let us learn about this method. So this is the differential equation which we have to solve. And using the approximations, if we substitute this y double prime and y prime back into this differential equation, we will get the equation of this sort. So we have simply substituted this expression over here, and for the y prime we have substituted it over here, and this is what we get. Now if we simplify this equation further, then we can see that we will get this. If we just take the common LCM, then this equation 2h square will be the common LCM, and this is what we'll get. So the first term over here will be multiplied with 2, the second term over here will be multiplied with h, and then the remaining terms will be multiplied with the 2h square, and this is what we will get. Now if we collect the coefficients of yi plus 1, yi and yi minus 1, then we can rearrange this equation into this form. So for the yi minus 1 coefficient, in the red we can see that it will be 2 minus h times pi. This is what we get. For yi coefficient in the black, we will have 2h square qi minus 4 from here, and for yi plus 1 in blue, we will get 2 plus h times pi, and this would be our equation. Now we can further rewrite these variables. Say if I take 2 minus hpi as the new variable, say k with a subscript I, this variable if I assume to be say m, and the last variable say as L, then this equation further simplifies to this. So this is the final, we can say, is the approximated differential equation making use of the central difference approximation. This is what we get. So now let us see how we can make use of this equation. So in order to solve the differential equation, we have been given the x and it is in the region A and B, and our aim is to determine the value of y at any x which is lying in between A and B. So at x equal to A, the value of y is given to us as alpha, and at x equal to B, the value of y is given to us as beta. And our aim is to determine the value of y at any intermediate points x. Now in order to do this, we have to divide this region into large number of intervals. More will be the number of intervals, more will be the accuracy. But to begin with, we will divide this region into say 2 intervals first. So if we divide this into 2 intervals, then we know the value of y at A, we also know the value of y at B, and now our aim is to determine what will be the value of y at this point over here, with the help of which we have divided this region into 2 intervals. So how this will be done? Over here we can say that the value of y, the running index, we can take for this point where we have to determine the value of y is 1. So at x equal to A, we say that the value of y is 0, and at B the value of y is 2, and at the point where we have to determine the value of y is 1 in the equations. And over here, since we are dividing this region into two intervals, then the step size over here will be given by b minus a by 2. And for two intervals, there will be just one grid point. This we can see over here. So our aim is to solve this differential equation. This was the reduced differential equation where we said that I can take any values 1, 2, 3 and so on. Now if we take the case where the number of intervals are 2, then we know that there is just one grid point where we have to determine the value of y. So over here for this case, when the number of intervals are 2, then I will be equal to 1 because there is only one grid point. So over here, if we take I as 1 in this particular equation, then this equation will reduce to this. So k1 y0 from here, then m1 by 1 and then l1 by 2 will be equal to 2h square r1 for this interval when n is equal to 2. Now we know that the value of y at x equal to a or I equal to 0 means y0. Y0 is what? Y0 is the value of y at x equal to a, which we know from the boundary condition is alpha. So we can put y0 as alpha. Then we will have m1 by 1 and then l1 by 2. Now what is y2? Y2 is the value of y at x equal to b, and which we know from the boundary condition again it is equal to beta. So we will substitute y2 as beta and y0 as alpha in this equation, and this is what we will get. Now from here we can rearrange this equation and then we can determine what will be the value of y at y1, which is the value of y at this grid point located at the position x equal to a plus h, or we can say y1. So y1 we can determine from this equation. We know everything. We know h, we know r1, we know k1, alpha, l1, beta and m1. So all these values are known. So knowing all these values, we can determine the value of y at this particular grid point when the number of intervals are 2. Now let us take the next case when we divide the given region into 3 intervals. So for 3 intervals we say that n is equal to 3. Now if n is equal to 3, then the step size will become now b minus a by 3. And how many grid points will be there? There will be 2 grid points. So we have this interval ab, and now we are dividing this into 3 intervals. So in order to do this, we need 2 grid points. So these will be the 2 grid points. And again, we know the value of y at x equal to a, which is alpha, and at b it is given to us as beta. And our aim is to determine the value of y at these 2 grid points. So again, if we take the values of I for the various points over here, then for the first grid point, the value of I is 1, and for the second grid point, the value of I is 2. And we have to determine the value of y1 and y2. And if we note down the position, the coordinate x coordinate for the first grid point, it will be a plus h, and for the second grid point it will be a plus 2h. So basically we have to determine the value of y at this grid point and at this grid point. So let us see how we can do it making use of the finite difference method. Again we have to make use of this equation which we finally got after we made use of the central difference approximations. Now for the case when we take the 3 intervals, now we have to take the value of I equal to 1. So corresponding to I equal to 1, we will get this equation. And if we take I equal to 2 in this equation, we will get this equation. So we will get 2 equations. We will get 2 equations. Why? Because now we have to get the solutions for the 2 grid points. So these are the 2 equations which we'll get. And over here, y0 is again, we know from the boundary condition, it is alpha. So we can put the value of y0 over here in this equation, which is alpha, and this is what we'll get. And in the second equation, if you look carefully, we know the value of y at 3. So y3 is known to us, which is beta. So if we substitute y3 as beta, the second equation will be like this. And if we rearrange these 2 equations, the first equation over here will be given by this m1 y1 l1 y2, and the k1 alpha we have taken on the right hand side. So we get this equation, and the second equation will be like this. Now these 2 equations can be written down in the matrix form, and if we write down the matrix form of these 2 equations, this is what we'll get. So our aim is to determine the value of y at 1 and at the second grid point, which we are denoting with the running index I equal to 2. So we have to determine basically y1 and y2. So now we have these two simultaneous equations and we can simplify it and we can get the values of y1 and y2. So we know all these constants over here from the given differential equation. So the values of these variables will depend upon the which differential equation we have to solve. Now let us take the case for the 4 intervals. So now for 4 intervals n will be equal to 4 and the step size will become now b minus a by 4 and there will be 3 grid points. So again if we look at the diagram over here, for the 4 intervals we'll have 3 grid points, and from the boundary value problem we know the value of y at x equal to a and at x equal to b, and the values of I, the running index for the 3 grid points, will be 1, 2 and 3 respectively. So these will be the x coordinates for the 3 grid points. So let us see how the equations would look like for the 4 intervals. So for 4 intervals we have to take 3 values of y, I equal to 1, 2 and 3 for the 3 grid points, and we'll get 3 equations over here. Now over here y0 is known from the boundary condition. So again y0 will replace with alpha in the first equation and y4 will replace with the beta in the third equation. So if we substitute the values of y0 and y4 in the equations, this is what we will get. And again we can rearrange these equations like this. So we get 3 simultaneous linear equations over here and we can put them in the matrix form, and this is how the matrix would look like. So again we can solve these equations using Scilab. We know how we can do it. So we can get the values of y1, y2 and y3 for the 4 intervals case. So this is how we can solve the differential equation using the finite difference method for 2 intervals, or 3 intervals, 4 intervals, and similarly you can extend it and you can solve it for any number of intervals. So now before we make the general program, let us see how we can solve the differential equation when the number of intervals are 2 or 3 or 4 using Scilab first. So for that we'll take the particular differential equation as an example and we'll see how this finite difference method can be implemented in Scilab. So let us take an example. Say we have to solve this second order differential equation with the boundary conditions given to us as these. At x equal to 0, the value of y is 0, and at x equal to 2, the value of y is given to us as this. And we have to evaluate the value of y at 1 for different number of intervals. And the exact solution of this differential equation is known and it is given by this. So the general equation which we started with was this, and if we compare the given differential equation which we have to solve with this general differential equation, we can see what will be the px, qx and rx for this particular case. So p over here we can see is 0 because we do not have any terms with a first order derivative. So p is 0 in our case, and q is equal to minus 1 because the coefficient of y is minus 1. So q is minus 1 and r is 0. Since x is lying between 0 and 2, so a is 0 and p is equal to 2 for this particular case. And from the boundary condition, we know that alpha is equal to 0 and beta is equal to this value 3.62686. So now let us see how we can do the programming in Scilab for 2 intervals case. So if we take the case when the number of intervals are 2, let us start with the programming for the case when the number of intervals are 2. So we are declaring these two variables, a is equal to 0 and b is equal to 2. Why? Because the x range is given to us as this x is lying between 0 and 2. So we take a is equal to 0 and b equal to 2. And from the boundary condition, we know that alpha is equal to 0. So we define this alpha is equal to 0 and beta is equal to the second boundary condition which has been given to us. So these values will vary depending upon which differential equations you are solving. Now since we are solving it for the 2 intervals case, so n we will take as 2. And we know from the discussion that the value of the step size h is given by b minus a divided by n. So depending upon the number of intervals, this step size will vary, and this is how it can be computed. Now since we have only two number of intervals, so there will be only one grid point. So we have to do the calculations only when I is equal to 1. So let me change this over here. This was the general program which we have made. Now I is equal to 1 because there is only one grid point, and for one grid point we know that we have to compute the x coordinate, which was a plus h. So we are taking this to be general, a plus I h, since I is equal to 1. So for our case x1 will be a plus h, and this is the exact value which we are also computing, because we will be comparing our computed value with the exact value. So y exact we are computing at this new coordinate, which is sine hyperbolic xi. Then P, we know from the given differential equation is 0, so we take Pi as 0. So since I is 1, so P1 will be 0. Q1 for this case is minus 1, so we are taking this to be minus 1. R1 is 0, so we take this 0. And then we compute the values of K, M, and L. So these were the variables which we had from the differential equation. So K was 2 minus HPI. So we are declaring this K as 2 minus HP1. So for I equal to 1, K1 will become 2 minus HP1, and M was 2H square QI minus 4. So we are using this equation over here to compute the value of M. And similarly, to compute L, we are using 2 plus H times Pi. And then this 2H square times Ri, we are denoting with the symbol B. So B is representing another new variable which is equal to 2H square Ri. So these all values will be computed for two intervals case when I will be 1. So for one grid point, all these values will be computed. And then we can compute the value of y1 from this equation which we just discussed. So this was the equation for two intervals case, and the value of y1 is 2h square times r1, which we have replaced with pi. So pi is nothing but it is equal to 2h square r1, and then minus alpha times k1 minus l1 times beta divided by m1. So this will give us the value of y1. And then finally we will be displaying the value of x, y, the computed value and the exact value. So now if we run this program, let us see what do we get. So we are getting the value, first value is x coordinate, then the value of y which we have computed using the finite difference method, and this is the exact value. So we see that these values are computed on the basis of the finite difference method. Now let us try to write down the program when the number of intervals are not 2 but they are equal to 3. So if we have to write down the program for 3 intervals, then we know that the number of grid points will become 2. So we have to compute all these values now for both the grid points, the first grid point as well as for the second grid point. And from the PPT we know that we have to make use of these equations. So since we have to do the calculations for the two grid points over here, so we will use the for loop over here, and for I equal to 1, 2, 2. And so this loop will work and it will do all the calculations for both the grid points. We have to solve these two simultaneous linear equations making use of Scilab. So we know how we can solve such equations. So for that we'll define the matrix A as this and the matrix B as this, and then using the left division operator we can determine the value of y1 and y2. So let me remove this from here, and instead if I write down the matrix A, which will be from here, it will be M1, then M, then A2 and M2. So this will be our matrix A, and the matrix B will become our B we have defined as 2h square R1. So B1 will be now, this will be B1 which we have computed over here minus K1 times alpha. And the second element will be 2h square r2. So this will be b2 from here. b2 minus l2 star beta. So basically we have to simply write down all these values as it is, which are appearing over here in the matrix form. So we can compute now the value of y. It is very easy to do using Scilab. So we have to just use the left division operator and that will compute the value of y. So this would be the program for, say, when the number of intervals become 3. So with this minor modification, we have written down now this program for 3 intervals case. So now let us run it and see the results. So if I execute this program, I have to save it first. And now run this program. So on execution, we see that we are getting these values of y. So the middle column is giving us the computed values of y at these x coordinate, and the third column gives us the exact value, making use of the sine hyperbolic. Now let us further extend this problem and see how we can further extend it for, say, when the number of intervals increases to 4. So when the number of interval increases to 4, we see that we have to simply make the changes in the matrix A and B over here. And since they will be for 4 intervals case, we have to do it for 3 grid points. So here, instead of 2, we have to write down 3 so that all these computations are done for all the 3 grid points. And then we have to make the corresponding change in the matrix A and matrix B. So if I change the matrix A to, say, as given here, so this is how. So I have to add this, and then the third row elements will be are K2, and then sorry, it will be K3, not K2, but it will be K3, and then M3. So the matrix A will be modified to this, and the matrix B will be, first element will remain same, second element will be only B2, and the third element will be B3 minus L3 times B. So with this minor change, this program now can be used for 4 intervals case. So let us save it first and execute it and see what do we get. So if I execute this program for 4 intervals case, I'm getting, sorry, over here I have not changed the number of intervals to 4. So make a change over here. Changing the intervals to 4, the step size will change, and accordingly these values will change, and this is what we get. So now if we focus at the value of y at x equal to 1, for 4 intervals we are getting this value and the exact value is this. And if we do the comparison of y at x equal to 1, when we computed it, when the number of intervals were 2, it was this. So we see that the difference over here is much large in comparison to the value of y when we increase the number of intervals to 4. So this error has become less. So as you'll increase the number of intervals further, the error will reduce, and now in order to do that we have to make the general program. So now we will see how we can make the general program so that it will work for any number of intervals. But before we do that, let us try to write down a single program which will work for 2, 3 or 4 number of intervals. So this is the program which will work for any number of intervals, which may be 2, 3 or 4. Here we have used the for loop, and for loop will run from 1 to n minus 1. N is the number of intervals. So if the number of interval is 2, this for loop will run only once because there is only one grid point. If the number of intervals are 3, then there will be 2 grid points. So this for loop will run 2 times. And for 4 interval case, this loop will run 3 times for 3 grid points. And here we have made a small change in the program. So if the number of interval is equal to 2, then this equation will work. And for 3 number of intervals, the matrix A and B will be used like this as we saw before. And for 4 number of intervals, we have to simply make the change in the matrix A and B, and this is how the matrix would look like. And we'll compute the y value using the left division operator again, and finally we'll display the value of the x coordinate, the y value which is computed using the finite difference method, and the exact value. So now let us run this program for all the test cases for 2 intervals, 3 intervals and 4 intervals, and see whether it is working or not. So I have made the number of intervals as 2, and if I run this program, this is what I get. So I'm getting the correct value. If I now simply change the number of intervals to 3, it should work again, and we should get the 2 values for 2 grid points. So this is what we are getting. And now if I change it to 4, then let us execute again. So we see that again we are getting the result for 3 grid points. So this program is a combined program which will work for 2 intervals, for 3 intervals, for 4 intervals. Now after this, we'll try to generalize it further so that it works not only for 2, 3 or 4 intervals, but it works for any number of intervals. So we will generalize this program further. So in order to write down the general program for any number of intervals, let us see how it can be done. So we have to generate the matrix A and B for the general case. Now the matrix A has the diagonal elements as m vector. The diagonal elements above the main diagonal are your L vector, and below the diagonal element is your K vector. And the diagonal elements is always equal to the number of grid points. So for 2 grid points, we have the 2 diagonal elements. For 3 grid points, we have 3 diagonal elements. For 4 grid points, we have 4 diagonal elements. And the order of matrix, if we look at, the A matrix is a 2 by 2 matrix for 2 grid points, 3 by 3 matrix for 3 grid points. For 4 grid points, we have 4 by 4 matrix. So the order of matrix is depending upon the number of grid points. So say we call G as the number of grid points. Now, in order to do that, to generate the matrix A, general matrix for any number of grid points, first of all, we have to create a matrix, zero matrix of the order, and the order of the matrix should be equal to the number of grid points. So how it can be done in Scilab? It can be done very easily making use of this zeros function. So if we use this zeros function, G by G, and if say the number of grid points we take as 2, then using this function, the 2 by 2 zeros matrix will be created something like this. Now finally we want A matrix to be this. So for this we have to add this matrix, and we have to make use of this diagonal function. And since we want the diagonal elements to be the m vector, so we have to simply add this. So if we make use of this function, then what will happen? This will be matrix will be added with the diagonal elements which is equal to the m vector. So this will be m1, m2, 0. So this matrix will be added. Now to this we have to add this L1 also. So for 2 grid points, L1, L2 for 3 grid points, and L1, L2, L3 for 4 grid points. So in order to make it general, what we have to do is we have to use again the diagonal function, but now here we have to add the L vector, and the L vector will be L1 for 2 grid points, L1, L2 for 3 grid points, and L1, L2, L3 for 4 grid points. So we have to use this over here. So the L vector starting from the first vector, which is L1, up to the G minus 1, because for 2 grid points we want just L1. For 3 grid points we want only L2. So it will be 1 up to G minus 1, and since we have to add these elements above the diagonal elements, so we have to make use of this function. So if we do this, then what will happen is this matrix will be added because we have used this one subscript. Now, in order to add the lower diagonal elements, we have to use again the diagonal function, and for that we have to use diagonal. Now, since we want to add the diagonal elements k2, k3, k4 and so on, so we have to add the k vector, and the k vector will start from the second element always, and it will go up to the last grid point. So it will run from 2 to G, and since we want to add it to the lower diagonal elements, that means the elements below the diagonal elements, we have to use -1. So we use -1 to add the elements below diagonal elements, and we use this one to add the elements above the diagonal elements, and you don't have to use anything over here if you wish to simply add the diagonal elements. So if I make use of this, then what will happen? This will be something like this. So this matrix will be added to this, and finally you see that if you add all these matrices, what you will get for 2 grid points, you will get n1 l1 and a2 m2. This is what we wanted. Now if you want to do it for 3 grid points, then this is going to give you the matrix which we wanted, and we wanted the matrix of this form, so we will get this matrix. We'll see when we'll execute this program. Now let us look at the matrix B. In order to create the matrix B, we see that when the number of grid points are 2, then we have only the 2 elements in B, which is this and this. For 3 grid points case, the first and the last element will be given by this, and the second grid point or the second element in the matrix B or the column vector B will be this. For 4 grid points, again the first and the last element is given by this, and second and third element will be given by this. So in order to do this, what we'll do is we'll create the first element of the vector B from here, and it will be done 2h square r1 minus k1 times alpha, and the last element of the vector B will be b1 bg. It will be your 2h square r times the last element of the r vector minus the last element of your l vector times b. So making use of this in the program, we'll try to write down the general program and we'll see whether it works or not. So let us come to the program now. So this is the general program we have written. So the initial statements are same. Here I've introduced only one new variable, g, the number of grid points, and the number of grid points will always be n minus 1. So for 2 intervals we have 1 grid point, 3 intervals we have 2, and so on. And this for loop will run for all the grid points that we have depending upon the number of intervals which the user gives. Now for n equal to 2, since we have just one equation, so we will write the same equation which we wrote before. But for the other cases when n is greater than 2, it may be 3, 4 and any value, then for that we have written down this general matrix, and it is this matrix which we have to understand. So A, we are creating the zeros by zero matrix, and the order of this matrix is the number of the grid points we have. Then the diagonal elements we are using the vector m for that. For the diagonal elements above the main diagonal elements, we have to use the L vector, and the L vector will run from 1 to g minus 1. And the diagonal elements below the main diagonal will be your k vector, and the k vector will run from 2 to g. And here the b vector, the first element of the vector column vector b will be given by this, and the last element of the column vector will be given by this. And so this is how you can make the general program which will work for any number of intervals. Now let us test this and see whether it is working or not. So we'll try for different number of intervals and we'll see whether we are getting the correct output or not. And here using this differential equation, the exact value is this. So let us run for different cases and check the output. So here I have displayed the error also. So let me remove this so that we can get the clear output. So I save this program and run it once again for 2 intervals. Let me clear everything for the clarity and run this program. So for 2 intervals case, we are getting this because we have just one grid point. So this is the x coordinate, the calculated value, and the exact value. Now keep on changing the number of intervals and let us test our program. So for 3 intervals, we are getting this result. Change the interval to 4 and again run. So we are getting this. So it is working for 2, 3, 4 as it was working earlier. So the answers we are getting exactly the same one. Now let us increase the number of intervals further. So if I give 5 intervals for 4 grid points, this is what I'm getting. So we can compare the calculated value and the exact value. So we see that now the error is getting reduced. So on increasing it further, it is working. And you can now run this program for any number of intervals. Let us run it for 16 intervals now. And we see that this is the result. So this program is working fine, and we see that the accuracy is also improving as we are increasing the number of intervals. Now the calculated value is quite close to the exact one for 16 intervals case. Now if I increase it say further, I won't increase it to very large value, Otherwise, the computation time will increase very much. So let us try for 32 intervals. So the accuracy is up to the third decimal place. So we are getting the accuracy up to approximately third decimal place, so it is quite good. So now this is the general program for the finite difference method. It will work for any number of intervals, and you can try it for different differential equations. So if you do it for any other differential equation, what you have to do is you have to make the corresponding changes in the values of a, b, alpha, and beta over here. You can give the any value to the number of intervals, and other thing which you have to make a change over here. You have to give the appropriate values to the p, q, and r depending upon which differential equation you are solving. Rest will remain same. So this is now the general program which should work for any second order differential equation for the finite difference method. So we have learned what is finite difference method, and we have also seen how you can implement this method using Scilab for 2 intervals, 3 intervals, 4 intervals, or any number of intervals.